Hi everyone, today we're going to continue on with chapter 6. We're going to be talking about the SN1 reaction today. So an SN1 reaction is going to proceed through a stepwise pathway. This is going to be a two-step process. An SN1 reaction is always going to have the formation of a carbocation intermediate. SN1 stands for substitution, nucleophilic, unimolecular. So unimolecular means that overall this is going to be a first order reaction. So unlike an SN2 reaction, a SN1 reaction is going to be called a dissociative mechanism. So what a dissociative mechanism really means is it means that a ligand is going to be lost to give an intermediate compound of a lower coordination number. So if we look at a general scheme of this, we start with our substrate here, and then what's going to happen is we're going to have the formation of our carbocation species or intermediate, which is shown here in X, plus our leaving group. So these are true intermediates, and again, they will have a positive or negative or can even be a radical. So after the formation of that carbocation intermediate, the nucleophile, which is going to be shown here as Z, is going to attack that carbocation and form our new product. Again, this is going to be a two-step process. So if we look at this more specifically, we have a compound as shown here. And what's going to happen is our leaving group, which is shown here as X, is going to leave our substrate. This is going to be our slow step or our rate determinant step. And we are going to have the formation of a planar carbocation intermediate. So that's important that it is planar, which we will talk about when we look at the stereochemistry, plus our leaving group, which will be shown here as X. So after we form our carbocation intermediate, we will have the attack of our nucleophile at that carbocation. So what's important about this is if we look at the carbocation, so this is sp2 hybridized, so this is going to be planar. So this is going to allow for either a front side attack of the nucleophile or a backside attack of the nucleophile. So we will have two different types of products for SN1 reactions. We will have an inversion product, which we talked about with SN2 reactions. We will also have a retention product. So drawing those products here, we have our inversion, which is from our back attack, and we also have our retention product, coming from the front attack of that nucleophile onto that carbocation species. So the rate equation for a SN1 reaction, as I mentioned, it's going to be first order overall. So it's going to be with respect to the substrate and then zero order with respect to the nucleophile. So when we write the rate law is going to be equal to K times concentration of the substrate. So the nucleophile is not going to be involved in the rate determining step. So therefore, it's not going to affect the rate of substitution. So this is why when we're looking at SN1 reactions, weak nucleophiles or weak bases will actually work for an SN1 reaction. Whereas when we looked at SN2 reactions, this was not a possibility because we needed a strong nucleophile for an SN2 reaction just because the concentration of the nucleophile affected the overall rate. So again, the rate for an SN1 reaction is going to depend only on the dissociation of that substrate into the carbocation and the leaving group. If we look at the energy profile for a SN1 reaction, so a couple of things we want to think about. So as I mentioned, this is going to be a two-step process. We know that the activation energy, the first activation energy, has to be larger than the second activation energy. And this again is because the rate determining step is step 1. The formation of the rate determining step is going to be endothermic because we have bonds breaking. So if we draw our energy profile again for an SN1 reaction, again, it has to be endothermic because we have bonds breaking. We know that our first activation energy is going to be larger than our second activation energy. So here we have a large first activation energy. Again, this is going to be our rate determining step. We have a smaller second activation energy. We have a transition state here, a transition state here. Here is where we have our substrate plus our nucleophile, so what we're starting with. In this position, we have our carbocation plus our leaving group plus our nucleophile. So again, this is where our carbocation intermediate is. And then our product is going to be when our nucleophile attacks our carbocation species plus our leaving group. So again, this is important that following the production of the carbocation intermediate, the nucleophile is going to immediately add to form the substitution products. So let's look at stereochemistry. So again, we're talking about stereochemistry for an SN1 reaction. So the stereochemistry of a SN1 reaction is going to be determined by that second step. So the second step, again, is when the attack of the nucleophile onto the carbocation. So I mentioned this before, since our carbocation is going to be sp2 hybridized, so it's going to be planar. So that means we're going to have this empty p orbital. So what can happen is this nucleophile is going to attack either from the front or from behind. So this is why we have the possibility of 2 different products. So again, we can have an inversion, which is going to be from a backside attack, and we can have a retention product, which will be from the front side attack. And this is, of course, is if the reaction is occurring at a chiral center. So let's look at some examples of SN1 reactions. So example 1, we're going to look at the synthesis of enantiomers. I think it's useful too to always locate your stereocenters and figure out the configuration at that stereocenter. So this will help you think about the inversion and the retention products. So again, our first step is going to be our rate determining step. This is our slow step. So we are going to have the formation of our carbocation. Again, this is going to be a planar compound because it's going to now sp2 hybridized. So what's going to happen next is we have the addition of our nucleophile. So our nucleophile is going to attack that carbocation, and we are going to end with 2 different products. So we can have our retention product. So our configuration is being retained. We have S configuration as our product, or we can have our inversion product. So now we have an R configuration. So again, this would be retention product, and this would be our inversion product. So the inversion product is probably slightly more favored just because the nucleophile attacks it so quickly that the leaving group does not have time to move away before the nucleophile approaches. So let's look at another example. So now we're going to look at the synthesis of diastereomers. So let's look at this compound right here. So something to think about or notice, we have this bulky tert-butyl group, and this is going to be done in water. So water is going to be our solvent, but this is also going to act as our nucleophile. So again, water is a weak base. However, it will work for SN1 reactions because the nucleophile is not part of the overall rate for an SN1 reaction. So first step is going to be our slow step. So this is going to be the formation of our carbocation. So after the formation of our carbocation, our nucleophile, again in this case is going to be water, is going to attack this carbocation. So this is going to result in the formation of retention product and a inversion product. So one thing you will notice is you should notice is that oxygen. So oxygen is going to have this plus formal charge. So we don't want oxygen to have that plus formal charge. So what actually happens is your solvent, so water in this case, will deprotonate one of those protons. So it's going to take this proton here, and it can take this proton here. So our end products are going to look like this. So looking at these two, we have our retention product here. We have our inversion product here. So the inversion product is actually going to be a major product here. And the reason for that is if you look at this bulky tert-butyl group that is pointing in front, so it's just going to be harder for the OH group or the water to attach as a wedge. So again, the inversion is going to be the higher or major part of our product. So just a side note, when we look at weak bases, so again, weak bases are going to proceed only SN1 reactions. SN2 reactions, they cannot proceed because of the rate law. So if we look at water, what we're going to actually add to the compound is going to be an OH. Another thing that you guys will see quite a bit are going to be alcohols. So if we look at something like methanol, what's going to actually add to the compound is going to be the OCH3. So what happens is the nucleophile, so water or methanol, is going to attack, and the oxygen is going to be left with that positive charge, as I showed in example 2. So when oxygen has that positive charge, the solvent, for example, water or methanol, is just going to deprotonate one of those protons to remove that positive charge. So this part of the reaction right here does not necessarily have to be shown unless the question is asking for a mechanism. If you're just asked to draw the products, you can just draw these two. So let me work on any of the chapter 6 questions dealing with SN2 and SN1 reactions. On the next lecture, we're going to start talking about some factors that can affect SN1 reactions, and then we're going to talk about resonance, and we're going to talk about something called carbocation rearrangements. So reach out to me with any questions. Otherwise, I will talk to you guys in a couple days. Have a great day, everyone.